has context, it has meaning, rather than being 15 or 4,625.38. So here's what we did. For every probability function beginning in chapter 10, going through classical mechanics, continuous and discontinuous system, we said, we're going to ensure that the probability of finding the particle, how is that done? Through an integral over all space from 0 to a. We're going to ensure that that probability is equal to 1. That's called normalizing. When we do that, that becomes b squared integral from 0 to a of sine squared n pi x over a dx. In other words, you take that wave function and put it in there. When you do this and set it equal to 1, you find out the b value ends up being the square root of 2 over a. All right, so we find several things. We apply boundary conditions, we reduce wave functions, we find some coefficients there, general coefficients. So we also, when we apply boundary conditions, we produce quantization. And then the last thing we do is do this probability business, and we find out that the last b in this particular value is determined. So we determine the unknown coefficients by boundary conditions and normalization all the time. Those are the fundamental principles that we're going to use going forward. Now, in the homework problem, we have 3, 4, and 5. I am very, very reluctant to assign 4 because it is so easy that all of you will completely mess it up. It's just kind of how it works. I can't give an easy problem because all of you just overthink it. So here's the problem. The problem, in problem number 4, the other ones we need to talk a couple of things through before we can talk about them, is I give you a wave function which has a normalization constant that is a superposition of different quantum states. So I have a wave. I don't know whether it's in the n equal 1 state, the n equal 2 state, or the n equal 3 state. Note the 1, 2, and 3 here. Here are the normalization constants, root 2 over a, root 2 over a, root 2 over a. However, I have assigned to quantum states 1, 2, and 3 weights to them. I have a 1, a square root of 2, and a square root of 3. So that is the different weight that is applied to those 3 superposed states. The first thing we need to do is to find out what this quantity or the new normalization constant is. To do that, I refer you back to the notes on page 8 and 9. Notice that here in 8 and 9, I added 2 states, not 3. I have an A here and a B here, which represents my 1, my square root of 2, square root of 3. When we then expand this and then integrate it, the cross terms disappear. Why? Correct. Why does this term go to 0? It's a beautiful question that you'd ask earlier. What's that? They're orthogonal because they were resulted from Hermitian operators. That's correct. All the wave functions are orthogonal, means if I integrate, and they are different wave functions, as you demonstrated in problem 1 of the homework, they go to 0. That goes to 0. These are individually normalized. That goes to 1. That goes to 1. We set everything equal to 1. So we find out that everything ends up here. That the integration of my superposed now wave function is an n squared, there's my n, that the coefficient that weights it, this a squared, b squared, is this 1 square root of 2 square root of 3. So how do we find then n squared? Well, n squared is 1 over, or n, 1 over the square root of the first coefficient squared plus the second coefficient squared, and in this case, the third coefficient squared. So in this particular problem, where these are the coefficients, here, 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 that give weight to the influence of each one of these, your normalization constant is 1 over the square root of 1 squared plus the square root of 2 squared plus the square root of 3 squared. And so that becomes, what, 1 over the square root of 6, if you do it. That's 1 squared plus 2 plus 3 is a total of 6. Now, the problem then goes on. It says, if we were to measure the system energy, that's why I wrote this down. Here's the system energy. Remember, you have your n in 1, 2, and 3. If we were to measure the system energy, before we make a measurement, remember talking about that whole business about making a measurement, prior to making a measurement, what the probabilities change? So before we make a measurement, what's the probability of measuring an energy value of 4h squared over 8ma squared? Well, I go to my energy expression. If n squared is 4, n is 2, right? For that one? Now, the probabilities are illustrated here. The probability of being in any particular given state is the coefficient multiplying that particular state squared divided by the essentially times the normalization constant. So for n equal 2, that's this state here. The coefficient weighting that is the square root of 2, so the probability becomes the square root of 2 squared over 6, or the normalization constant squared. Or 2 over 6, or 1/3. So we have 1/3 probability of making a measurement and finding it to be in that quantum state. Then we do make a measurement. When we do make a measurement, it says if the energy is measured and it is found to be 9h squared over 8na squared, what is the wave function for the system? If we make a measurement, these probabilities change. Just like when we asked with Mr. Jones' first, second son, a boy or a girl. Once you make a measurement, the first one is a boy, the second one becomes a 50-50 child. So in this instance, we have now made a measurement, and we determined this n squared is 9, making n 3. That means all these coefficients here, here, and here change. When we pulled letters out of a Scrabble box, when we took a letter out and it was an S, the probabilities of pulling out a different S was now have changed. So for the case, we made the measurement. We had n equal 3. That means this coefficient goes to 0. That coefficient goes to 1, or 0, and that coefficient goes to 1. So that ends up being the wave function of the system.
Is that because when you square it, that's 3 and the other 2 are not?
Well, the 1, root 2, root 3 are gone. They no longer exist anymore because we made a measurement. We made a measurement, the system collapsed into this energy state where n was equal to 3. We now know it was not an n equal 1, it was not an n equal 2, it is an n equal 3. So the probability becomes a certainty.
Is the normalization constant still there even though the other 2 terms go to 0? Or after we make
It is, but the normalization constant becomes 0, 0, 1. So that's the effect of making a measurement. All right, now, I wanted to go through that because it's easily confused, but it's a simple problem. Now, I want to change, we had this particle in the box system, we have two systems I want to look at. One is in your homework, and one is in the notes. So let's take a look at those. In the notes, I've got this. We have now a barrier, important, tattoo it to your forehead, in reverse, you can see it in mirror. The potential energy here in this region, from 0 to A, is finite, not infinite, okay? So here's what I've got. I have a particle incident on this barrier, okay? I have then a possibility that the particle will appear on the other side of that barrier. Then we have a particle within this region, okay? Now, I want to solve the quantum mechanics for this. Now, here, we have a potential V equals 0. Over here, V equals 0, and then we have a V equal A, I can't remember what I call it, okay? So we have a potential here, no potential here, no potential here. This, in this region, is essentially the free particle problem. Because you have no potential, you've solved it several times. So I'm going to call this region 1, region 2, and region 3. So the wave function in region 1 is going to be A e to the I kx plus B e to the minus I kx. Essentially the free particle problem. Here is the interpretation of this. Here with a positive I k, remember K is momentum. So this is interpreted as the particle traveling with a forward momentum. This is a particle traveling with a reverse momentum. In other words, that second term, it would be a reflected particle. So I want to know how much of the particle is reflected, how much goes through. Okay? So the first wave function of this region is a traveling particle. Similarly, in region 3, so I'll go A, B, C, D, this is E times e to the I kx plus f e to the minus I kx. Over here, there is no potential energy. It is essentially a free particle problem again. Within this region, which was the subject of an exam problem, here we have a particle such that the energy of that particle is less than the potential, I'll call it V naught or whatever value I got. What you should have discovered in the exam problem is that the energy of the free particle would be V naught, if energy less than V naught. You get then real exponential solutions. So psi 2 becomes now C e to the Rx plus D e to the minus Rx. The R is different because you have a potential energy here. And the exam problem was intended to elucidate that. So you have then, for this, your K, where's my K? The K, just like the free particle problem, was the square root of 2me over h bar squared. But when I have now a Schrodinger equation that has a potential in place, that one, when you solve it, the now coefficient here becomes, notice that this is V naught minus E. E is less than V naught, making that constant positive, which it requires. So R becomes V naught minus E, 2m over h bar squared, square root. So they're subtly different. Okay? So when we solve the Schrodinger equation, we get then the real result. Now, we have a ton of coefficients here. A, B, C, D, E, and F. I'm going to start making some arguments. One, just by practical matter, the problem illustrates or suggests that we have a particle incident from the left to the right. So there's a possibility, there's a probability the particle will go forward and the probability that will go in reverse. So A and B will be those probabilities. There is a probability that the particle will exist in this region. It will be finite because this region is limited from 0 to A. If this A were to infinity, this term would explode and C would be 0. That is not the case here. The particle exists, the region is finite, so C and D both exist. Once the particle has appeared on the other side of that barrier, it will move forward. There is nothing over here to cause the particle to move into reverse. All right? So from the design of the question, the design of the problem, I will artificially set F equals 0. Because the particle will not move in a reverse direction in region 3. That's simply an argument on my part. Now, to get the A, B, C, D, and E, we need to apply boundary conditions. Now, continuity is our criteria here. What would be the boundary condition, the existence of the wave function at 0? Is that? It would be 0 if this potential were infinity. It is not. So the wave function can exist in this region. So it is no longer 0, because the wave function is not 0 in here. So we have to have continuity. The continuity requirements are that the wave function in region 1 at 0 must be equal to the wave function in region 2 at 0. But that's insufficient, because continuity, even though they match, is not assured. If I have a boundary and I have a wave function that comes up like this, and then it comes down like that, that is a discontinuity, even though they have the same value at that point. So there's a second criterion for continuity. Not only does the value have to be the same at this boundary, the slope has to be the same. In other words, the first derivative. So we have the second condition is that d wave function 1 at 0 dx has to be equal to d wave function 2 at 0 dx. These are the two continuity requirements. Okay? We now ask the next question. What are the next boundary conditions? Well, we have to apply those very same conditions for this position A as well. Same thing. We have a wave function that can exist in this region and can exist over here, so there, by the first postulate, has to be a continuity requirement. So we have that the wave function in region 2 at A has to be equal to the wave function in region 3 at A. That doesn't guarantee continuity, so we have to do the derivatives as well. So the derivative of psi region 2 at A dx has to be the derivative of psi in region 3 at A dx. These four continuity requirements, I will just do a couple of them. For the first one, psi, if I put 0 in for x, the first one, this produces A plus B. If I put 0 in for this, it becomes e to the 0. 0 into the e to the 0 over 1. So I get A plus B. Then it has to be equal to this, where x is 0 as well. Well, that becomes e to the 0 as well. So it becomes equal to c plus d. Let me do the first derivative one, then I will show you the results. For the second boundary condition, we have the derivative of this at 0, so that will give I, K, A, e to the 0, minus I, K, B, e to the 0. That's the derivative of this. evaluated at 0 has to be this, which is RC e to the 0 minus RD e to the 0. So you see how that works. Here, I would just simply put A in for here, so C e to the RA plus D e to the minus RA has to be equal to E to the IKA. That gets a third one, and then the derivative, of course, will be the fourth one. Once you do that, you produce the following 4 then results. So here's the first one, A plus B, C plus D. Then we have, there's the value at A. Here's the derivative that I did at 0, and here's the derivative at A. We only had just this first term. Now we have 4 equations. We have essentially 5 unknowns, but I can solve for one of them. This is a lengthy algebraic exercise. I promise I will not make you do it. But if you do produce that result, you come up with this expression for the coefficient E here, where E ends up being this combination of A, and you have the R, K, here's the length of the box, A, and you get this, it's a lengthy, you gotta do several pages to get there. So here's what we'll do. I'm going to define the probability of the particle being in region 3 divided by the probability of the particle in 1 moving forward. Here's where that previous homework problem that I elucidated comes into play. The probabilities are the coefficients squared. So the probability of the particle moving forward in region 1 is that coefficient squared. The probability of the particle moving forward in region 3 is that coefficient squared. That's why I expressed the E coefficient in terms of the A coefficient. It was just multiple equations solving unknowns. So if I define my transmission coefficient as the E squared divided by the A squared, notice both of those have the same normalization constant, so the normalization constant disappears. So we have this. So I put an E squared in here, I divide by an A squared, I can express them, the coefficients go away, and the transmission coefficient becomes always a very, it's, again, another very complicated that I will not make you do unless you make me angry.
If it had been the probability of being in region 1 with the momentum going backwards, would it have been over B squared?
Correct. So if I wanted now the reflection probability, I would do A squared over B squared. Or B squared over A squared, I guess that would be. So the B squared is going backwards, the A squared is going forward. So if I wanted to problem what fraction of the wave function is being reflected, I would do a B squared, reflected one, over A squared forward. So yes, you are correct. So we can do it in any way we like. So there's the worst case. This is a non-zero, or is always greater than 0 value. Everything is squared. So with that, I just simply present results. So in here, I will do an example. I'm not going to make you do this, but this is an illustration of what tunneling is about. I want to plot the transmission probability. What's the probability of the particle making it through? If I have a 5 electron volt barrier, that's how high the barrier is. It is 100 picometers wide, and I have an electron that is incident that is variable in energy. So we have that in case. So I take my function that I had above, this ugly one, I make a function out of it, and then I plot it. All right, so here is the energy of the electron. The barrier height is 5 EVs and 100 picometers wide. So when I have an electron energy of 0, none of it gets through. But look at this right here. There is your 5, that's the height of the barrier right there, 5 EVs. So below 5 EVs, the probability of the particle appearing on the other side of the barrier is a non-zero value, and it's climbing steadily. Even at, this is what's most interesting, at 5 eV. Think about classical. What would a classical depiction of this look like? It would be 0, 0, 0, 0, 0, 0, 0, 0. And once it hit 5, it would go to 1. Right? That's what classical should do. But it gradually climbs. Even at 5 EVs, the transmission probability is just slightly less than 0.8. So even above, like say, even 7.5 EVs, now the energy, the electron is well above the barrier. There is a probability that there's about 0.85 or 85% of the particle appears on the other side, about 15% of it is reflected. But once you get the electron energy sufficiently high, it goes to 1 as it should. Do another example. What if I have a 4 electron volt electron? I want to plot the transmission probability as a function of the barrier height. So now the barrier height goes from 0 to 30 EVs. The electron is 4 EVs, and once again, initially with a 4 EV electron and a 0 barrier, all of it goes through, makes sense, but it begins to drop. So here's our 4 EV, 4 EV electron. There's the barrier height at 4 EVs here, and we get that same kind of about 0.75, 0.25 reflection, and it goes down in kind of steady fashion. And then finally, the last one, if I make an 8 EV electron, a 10 EV barrier, and I change the barrier width. So the barrier initially has 0 width, no barrier. We have 100% transmission, but as the barrier gets wider and wider and wider and wider, the transmission goes down, but in a continuous fashion, and finally we get the barrier wide enough, it drops down to 0. This is the basis of integrated circuit chips. Integrated circuit chips have oscillating barriers that look like this. They have up and down and up and down and up. It's digital. So the current that occurs in a circuit is largely, there's a lot of tunneling that is involved in that. There is a microscope made from this. A microscope had a probe, essentially. It had a voltage in it, it had electrons in that probe and current. And the probe would go down near a surface. And the surface, then the electrons would tunnel through the barrier to the surface and would create a current. That allowed the measurement of extremely fine values. Here are some images from what's called a scanning tunneling microscope. This one is one of my favorites. This was a set of, I think, iron atoms, or adsorbed iron atoms on a surface of nickel, I believe. Let's go back and look at that. So what they were able to do, this is the IBM Algorithm Research Center, they were able to individually align iron atoms one at a time next to each other to make a circle. Look at what happens. Here's the initial formation. Here's all the iron that's on the surface. Notice over these, see how kind of a crystalline and regular it looks? You know, crystals and lattice structures that we talked about in chapter 7. Yeah, I know you slept since then. But there's a regular pattern in crystals, a positive, negative, and things like that. Well, this is very crystalline looking out here. So they begin to assemble these things. Now they get a little closer, and we have these kind of things. There's starting to see some things happening with it here. Then they get the circle even closer, and they finally close it up. Look at that. This is electron density within here. It's like you dropped a pebble in the middle of a circular pond. You have now put boundaries on the wave. You have now created interference patterns in a wave form. It still looks crystalline out here, but once within here, we have now standing waves.
So the quantum tunneling produces the current.
That's again?
The quantum tunneling is the one that produces the current.
Correct, correct. They get that probe close.
How does that work when the world works in classical mechanics? Like, where is the barrier between classical mechanics and quantum mechanics?
You do it, when we saw in the particle in the box system through fact that once you bring quantum levels up, increase the masses, increase the energies, make things bigger. When you do that, the quantum level and the classical level merge. That's called the correspondence principle.
What about, isn't there one point where you were saying that quantum and, is that a point where quantum and classical meet?
That's correct.
So this is where it meets, where we
Well,
can see it?
no, now we're down on the quantum level. We've not gotten to, this is well out of classical range.
Okay.
They're well out, because we're now on the atom by atom, I mean, we're down in the quantum field within here. But it's just amazing to see, and there's some other ones here, let's see if I have. That was first published in the New York Times. This was a xenon atoms, where IBM aligned the xenonide atoms to spell out the letters IBM. So that was I don't know, just some, femtotrillionth of a distance. Here's another corral where they put them on a different surface, and they make different shapes out of that. Here's another kind of a view of the one I just showed you. It's just amazing. Look at that. Look how the waveforms come into play. And then this was kind of interesting. If you look at, here's graphene. We've already suspected that graphene was a hexagonal, fused ring system. Well, now you can actually see it for the first time. So we actually have that ring system. One I think is really fascinating is here's a series of fused rings, and we always do this quantum delocalization, and the organic chemists talk about the delocalization of electrons from single and double bonds and all that, but they're wrong. They would put the electrons uniformly across this fused carbon ring system as a hexagonal ring, hexagonal ring, hexagonal ring, all fused together, and they're aromatic rings. But we see electron density appears more on the ends, and you can actually visually see it. Now, when you do the quantum mechanics, you get the correct result. The organic chemists just don't know that. So, and here's just kind of a difference. So here's the ring system, ball of stick model, and these are at 5 angstroms, and here we're getting down to higher electron, and these almost look like bacteria at this point. That's how these molecules come into play. So there's an amazing microscope that came about from the phenomenon that we know from quantum tunneling. So that was an important view in there.
What is it about quantum tunneling that produces the current?
What produces the current?
What about quantum tunneling that allows the production of the current? Like, is it?
If you have a probe, there is essentially, in a vacuum, there's a barrier, a potential barrier for the electron to go from the probe to the surface. So that classically it should not be able to go there. Quantum mechanically, electrons are extremely leaky. So they leak up from that probe down, and you actually produce a minor, very, very light current, which is now measurable. All right, now, with that, so I wanted to illustrate the tunneling. We're moving on a little bit. We have our two-dimensional system. We've covered a number of different concepts and philosophies. Now we want to start talking about translational energy. So I want to put the particle now, instead of a one-dimensional box, a three-dimensional box. In other words, this room. In this room, we have essentially a three-dimensional particle in a box system where I have an X, a Y, and a Z. So here's our room, here are the walls. This could be, by the way, a crystal, a zeolite crystal or something. I can house electrons in very small spaces, but we can have them in boxes as well. The Hamiltonian now, we have a single particle in three-dimensional space. So now I have a Cartesian Hamiltonian, which has a second derivative in X, Y, and Z. As was the case, you cannot solve that differential equation until you separate the variables into three wave functions. So we do what you did in the homework. I had you do a wave function in X and Y, separated into two different components using the separation of variables technique. Here it is done in 3 dimensions. So in 3 dimensions, I presume that the wave function, which is now a function of X, Y, and Z, now can be expressed as a product. This is important, product of the wave function only in X, only in Y, only in Z. Since the operators, the first operator operates only in X, I can separate out the Y and Z. This one operates only in Y, I can separate X and Z, and so forth. I get 3 different independent x, y, and z derivatives that all are equal to the total energy, a constant. So that means each one of them, this term here, just like you did in the homework, that's why I assigned that one. This term here, this term here, this term here must individually be equal to a constant. We know these are energy expressions, so we find out the first term here is equal to the energy in x, second term, the energy in y, and the third term, in energy in z. And they all add up to the total energy, so the wave functions then are identical. Notice the wave function, they're exactly the same for the x, y, and z, but now since we have 3 dimensions, we have 3 quantum numbers. We have to have a quantum number in x, y, and z, so I call it nx, ny, and nz. All are going to have the same normalization constant, but we are not guaranteed that this room is a cube. If the room is non-cubical, then the A is a different value than the B width, which is different value than C height. So they have you A, B, and C, which are the dimensions of your box. So the total wave function solution, wave functions multiply. This is an exam question you're going to get. I'm telling you right now, this is an exam question. I'm going to give you a wave function. You produce the total. Multiply them. If you add them, I will make you a business major, I swear to God. All right. The energies, though, add. Wave functions multiply, energies add. So the total energy, if I extract out the h squared over 8m, I have nx squared over a squared, ny squared over b squared, and z over c squared. Or if the box is cubical, I will extract out the a, b, and c as the same value. So I have h squared over a squared, then I have nx squared, ny squared, and z squared. Now, this is the subject of homework problem. Equally easy as homework problem number 4, so don't mess it up and try to make it complicated. It's homework problem number 3. In this, let's look, I ask you to, in problem number 3, determine the degeneracy of the 12 lowest energy states. Let's take a look at that problem. In the 12 lowest energy states, these are the energies right here. Now, I'm going to call this is just how you can do it, I'm going to call this value a constant, I'll call it K, just for convenience. So let's say that for the moment, my energy is equal to K times nx squared plus ny squared plus nz squared for a cubical box, okay? The first energy state has got to be the lowest quantum numbers. So the first energy state is going to be K times 1 squared plus 1 squared plus 1 squared, or 3K. It is non-degenerate. There's an energy state, there's only one quantum state that has that energy. Let's look at the next energy. So this is 1, 1, 1. The next energy state will be 1, 1, 2. This will be equal to K. I have 1 squared plus 1 squared plus now 2 squared. So that's 4, 5, 6. That ends up being 6K. Now, because of this here, this will be equal to the energy of 1, 2, 1, where I make that to 2, and equal to the energy of 2, 1, 1, where I make that one 2. So in other words, for energy 6K, there are 3 quantum states. One with a 1, 1, 2, a 1, 2, 1, and a 2, 1, 1. So we say that that energy state is 3-fold degenerate. That's the term, 3-fold degenerate. Then I have you in this problem continue up. Then you do maybe a 1, 2, 2, or 1, 1, 3, whatever. Just find all of them up to the first 12 energy states. So if we look at, for example, let's look at energy 1, 1, 3, and an energy of 1, 2, 1. Here, this is gonna be K, 1 squared plus 1 squared plus 3 squared. So that 3 squared is 9, so you get, for this, 11K, right? Let's look at the 1, 2, I'm sorry, 1, 2, 2. For the 1, 2, 2 state, I've got a K times 1 squared plus 2 squared plus 2 squared, according to the energies. So that's 4 plus 4, that's 8, plus 1, 9, so I get 9K. So this energy is lower in energy than the 113. Both of these are threefold degenerates. I can have a 131 and a 311. Here I can have a 122, a 212, or a 221. But look at 123. 123 is K times 1 squared plus 2 squared plus 3 squared. So this is 9 plus 10 plus 4, so I get 14K. What is the degeneracy of that energy state? Because now you have a 123, a 132, a 213, a 231, a 312, and a 321. So that's a big sixfold degenerate. Okay, now, so just find the first 12 below and just find what their degeneracies are. This expands, obviously. Now let me ask you this. This is very, very important. What happens if the box is no longer cubical?
Change coordinates?
The degeneracies disappear. They disappear. That's part of the problem there. This is how we will lift. It's called lift degeneracy. This is what is done like NMR, for example. What we're going to find is that energy levels are, they're balanced, there's degeneracy that occurs. We're going to find degeneracy, particularly in rotation. How do you get rid of that degeneracy? Well, look at Sturm and Gerlach. We'll talk about that pair later. What originally happened, they put a particle that had no magnetic fields in it. We'll see about where they come from later. So a particle with no magnetic fields. They put it through a magnet, and what happened, the particle split, one went up, one went down. That was the original discovery of the concept of spin. It's not spin, you'll find out later, it'll make your mind go. All right, so, but what they did, because the spin levels, spin up and spin down, and by the way, there's 4 of them, not 2. The spin up and spin down were the same energy, roughly modelized here, we'll get to that. But for the first approximation to the same energy, so they were essentially degenerate. Spin up and spin down in the same energy. They were degenerate, twofold degenerate. When you put them in an asymmetrical magnetic field, some of the particles aligned with the field, some against the field, you lifted the degeneracy. So symmetry, here's the bottom line, symmetry creates degeneracy. Lifting or making the system asymmetric removes the degeneracy. And that's what we use in spectroscopy, in NMR, and magnetic fields, and a variety of different things there.
How would one remove degeneracies?
What's that?
What is the point of removing degeneracies?
So that you can study the system. So, like for example, to remove the degenerate in spin, we discover nuclear spins. And if we know nuclear spins, that allows us to produce an NMR. Or electron spin resonance, ESRs. So putting things in magnetic fields, and we're going to find this about your rotation as well. But putting things in asymmetrical types of systems will allow you to study the quantum states individually. You separate them, in other words. Yeah, it's a very important thing. So that's the case within there. So in that now, here's the last thing we need to do in here, and then I'm going to go over the last problem. This is the three-dimensional quantum system. It's just a one-dimensional system times 3, the cube, right? The question I'm going to ask for this, the next one, and the system after that, and systems after that, is, on average, at thermal levels, remember thermal levels are defined by Boltzmann's constant times temperature. That is the energy around you in the room. Remember we were talking about in the probabilities chapter, in chapter 10, about the problem of having discontinuity, where if I had this system that looks like this, and something like that, and we said, well, can we treat it as continuous or not? Well, it kind of depends on how big those blocks are. Well, now I'm asking, how big are these blocks? Are the quantum levels in a particle in this room, and I'm going to make it a 1 cubic millimeter box. That is gargantuan to an electron. So I have a 1 cubic millimeter box. I'm going to actually use a helium atom. Are the quantum levels this far apart? Or, in other words, big? Or are the quantum levels very, very, very close together, which would make this continuous? To do that, I just do this a hand-waving kind of an argument, but we will do this more precisely later when we do quantum statistics. I recognize that if I have this E as this h squared or 8ma squared, nx squared, if I just rearrange this, well, I just had nx squared, ny squared, and z squared, I get this energy quality here. That's essentially the equation of a sphere. What I do is, in this hand-waving argument, I won't go through it all, but I'm just going to be presenting this argument. I create a sphere. This is two-dimensional representation, but now we're talking about 3 dimensions. Quantum numbers are all positive. So within this positive octant, this is a quadrant in 2 dimensions, but in a sphere, it's 1/8 of it. So I have so many quantum numbers, or in other words, quantum states, within this energy, which is kT. So if that energy is kT, I'm asking the question, how many quantum states are there underneath the value of energy of kT, the energy in the room? Okay? Again, it's just kind of a hand-wave argument. We will do this precisely later. And going through that, I want to ask the number of quantum states that are thermally available at kT. I do that at 300 Kelvin. I use the mass of, I believe, a helium atom. And I find, helium. I find out that for an energy at 300 Kelvin, I have an energy average of K times T. The number of quantum states in a 1 cubic millimeter by millimeter by millimeter box, there are about 10 to the 21st quantum states. So there are a huge number of quantum states that are thermally available, energetically available in this, in this cubic millimeter box. If I then ask the question, well, what is the energy difference between those quantum states? Is the energy difference big, or is it very small? If I do that computation, I take this 10 to the 21st, and I find out what is the energy difference, it's about 10 to the minus 28, which is about 1 billion times smaller than the energy in this room. Even more, actually. That tells me that our quantum states translationally look like this, not like this. That means I can treat translation continuously. It means I will use intervals instead of sums, which, by the way, is why the classical Boltzmann distribution was so accurate. It was so good because translational quantum states are so close together that they can be treated like classical particles. All right, so that's going to be an important thing going forward when we finally put the statistics arm to this. The last thing I want to do is go over your homework problem, and it's going to go along this scheme that we did here. Your homework problem is a model for a hydrogen molecule. It looks like this. The first two problems, 3 and 4, are very, very simple. This I want to guide you through. Over here, we have a potential of infinity. In here, we have a potential equal 0. And here, we have a potential equal to V0 or something like that. All right. First, in this problem, find the quantum mechanics or solve for the wave function in each of these three regions. In here, the answer is trivial, the wave function is 0. Over here, again, this is somewhat of a wave particle problem, but since it's bound, the wave function, again, do the math, verify this. The wave function in what we'll call region 2 is going to be your A cosine, you'll have your kx, and B times the sine of kx. That's the correct answer. Your wave function in region 3, where energy of your particle is less than the potential, will be real, and it will be equal to C e to the Rx plus D e to the minus Rx. This potential is assumed to go to infinity, to the right, which by then first postulate, the wave function must be finite. You will make the argument then that C is equal to 0 to require that the wave function be finite. So what's going to happen here is you're going to have a bound wave within here, and it's going to decay into this region. So now, what are your boundary conditions? List them. Based on the arguments that we've made in the tunneling probability and the particle, the 1D particle in the box. List the boundary conditions for this problem.
Sine 1 and 0 has to equal sine 2.
Exactly right.
And then the derivative.
And that's equals 0. Correct. Give me another one. That, by the way, gives us, for 0, that gives us A equals 0. So that produces psi 2 as being to B times the sine of kx as an answer. Okay? Does that make sense? So if this has to be 0 at 0, same as the particle in the box. I put 0 in for here, we get 0. I put 0 in for here, I get A. So A has to be 0. Give me another boundary condition. We got 47 seconds.
There's essentially the same one, but with A's.
Okay. Except because this potential is not infinite, we have a value. So you have psi region 2 at A is equal to psi in region 3 at A. And continuity requirements require that psi 2 prime at A, that means the first derivative, is equal to psi in region 3 first derivative at A. Okay? Those are your boundary conditions. When you do this, you're going to come up with a term that has a sine and a cosine. You have E and D. Divide them, you will get a function that is a tangent. And I'm guiding you through that to give you what the function should look like. When you do that, you should have a tangent function, and you have an energy on the other side. At that point, when you get the equation that's presented to you in part C, then you're going to have to do numerical work. You can't solve it by hand, so you'll need a solve block. So I want you to find how many energy levels there are, quantum energy levels are there for a particle in this region. And you get, I can't remember, 6, 7, 8 or something like that. So given the potential, given the values that I get, calculate how many energy quantum states there are. This is what we're going to find vibrationally. This is going to fit this. And we'll see when we look at vibration very soon. So you'll solve those for those particular energy states. But that'll kind of give you a little bit of a head start on it. But it's all about finding the wave function, establishing boundary conditions. Solving says we do this over and over again. I have a new schedule up, by the way. So if you go to the website, I posted kind of a reordering given our snow day. which I hated. I hate snow, dirty, messy,